Hi everyone, welcome to GemChem. Now today's video is on heterocyclic compounds part 2 video, and here we are going to deal with the structure of pyrrole. Now before starting, already one video is uploaded in channel. You can watch it. I will give the link in the description box as well as the I button present above this video. And if you are new to GemChem, don't forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. Now what do we mean by pyrrole? We are going to have a 5-membered ring with one nitrogen in it. And in the previous video, we have already dealt with 6-membered ring including nitrogen, that is pyridine. So the formula for this one is C4, we can write it as C4H5N, right? And this is actually isoelectronic with another moiety, which is our cyclopentadienyl anion. Now as you can see, there is 5 members in the ring. Similarly, in this case also there are 5 members in the ring, but this is neutral and in this case it is charged. So this also happens due to the nitrogen. Neutral because the nitrogen has a higher charge in it, as well as the consequence of nitrogen is that due to presence of this nitrogen, this part loses its radial symmetry. The symmetry is being lost. Similarly, the next case what happens is that it do not have 5 equivalent mesomeric forms, that is the resonating forms are different for pyrrole, whereas in case of cyclopentadienyl anion, the resonating forms are actually similar. So let us look into the different resonating forms. So if you can see here, this is our pyrrole. So one of the bonds come here. So what is our first work? This bond comes here, but during resonating structure writing, we do not generally use arrows, but in order to make you understand, we are doing so. So first it can come, or from here the lone pair present in the nitrogen can also go in this way and this can open. So which one has occurred? Since negative charge has come in the second carbon, so the pink one has occurred. We can say that from nitrogen, lone pairs are being donated in the next part, and as a result of which this bond has opened up, right? So here negative charge has come, and as nitrogen is donating its lone pairs, so we can say that it is having a positive charge. Now this negative charge is being donated at this bond and this one opens up, right? And now we can see here a negative charge and here a bond, right? So next step will be again the donation of this negative bond, right? And this can go on to get this one again. Or else instead of this one, if we try another path, that is if we try to open up like this, here it is being donated and this one opens up. As a result, this structure is formed. Again this negative bond, this negative charge is being donated here and this bond opens up. So another one is being formed. So we get 5 mesomeric structures. Now these resonances actually leads to the establishment of partial positive charge over nitrogen and partial negative charge over carbons. And which carbons to be focused on is 2, 3, 4 as well as 5. So each carbons are having the negative charges, right? So we can say that resonance has led to the establishment of partial negative charge on the carbons and a partial positive charge on nitrogen. Of course, we can see that inductive effect of nitrogen is always away from the carbon, right? Since it is away from the carbon, we can write that inductive effect is like this. From carbon to nitrogen, right? This is plus I from carbon and this is minus I for nitrogen, right? And mesomeric effect always acts on the opposite direction, that is nitrogen tries to donate the electrons, right? So we can say that this is plus M and always we know that plus M or mesomeric effect dominates, as a result of which we can say that there is two opposing effects, of which mesomeric effect is more significant. As a result, the dipole moment is away from the nitrogen. We can say that dipole moment is away from the nitrogen, and it looks like this dipole moment. And if we consider about the lengths of different bonds, 3,4 bond is very much longer than 2, 3 or 4, 5 bonds, but appreciably shorter than normal bonds. So write it down. Why this is so? These are normal. The normal bonds have sp2 hybridization, right? But in this case, along with hybridization, we are seeing a partial negative charge presence, again a double bond. So there is a dilemma between double bond and a single bond. As a result, there is difference in the bond lengths. Now, these electron drift, which we can see away from the nitrogen and towards the carbon, that is 5-membered heterocycles, makes them electron rich, because if we see dipole moment is from nitrogen to carbon, so we can see that the lone pairs present in the nitrogen is always being donated in the sextet or the resonance of the ring, as a result of which we can say that this ring is actually told to be as electron rich or pi excessive ring. Remember this. Now we are going to see the different moieties which will tally with this one. So first of all, if we compare this one, this is our pyrrole, right? And its analogous thing without double bond is pyridine, right? And so here we can see that what happens. See here, in this case dipole moment is from this direction, that is 1.55 D. But in this case it is in the opposite direction, because here only inductive effect is being acting, but here both inductive effect as well as mesomeric effect is acting due to double bond, right? So here it is 1.57 D. Now if we see the different bond lengths, then we can tell that this bond length, that is 3 and 4, is 1.43 angstrom. Next one, that is this bond length, is 1.37 angstrom, and the last one, which is this one, is 1.38 angstrom. So these were the different aspects of structures of pyrrole. Now in the next video we are going to deal with structure of thiophene and furan. So this much for today. Hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment if you like these videos.